Okay, so you're being recorded. So here you can see this is a problem that deals with compounds and elements, and that's where we had left off last time. So here you're supposed to identify whether each of the following is an element or a compound. Bromine, Br2, and hydrogen peroxide, H2O2. So here for Br2, you're going to say this is an element, basically because we have one type of symbol. Which is Br. Now, this particular element happens to come in pairs. You can't find individual bromine atoms by themselves. You always find them in pairs. There are 7 elements like that where you always find them in pairs, and they are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. So you notice that for iodine, I said iodine, not iodine, because when you say chlorine, bromine, iodine, fluorine, it's very consistent. If you want to say iodine, then you got to say chlorine, bromine, iodine, and fluorine, which sounds kind of weird. Now, some people remember this because they sound it out, Hänkelbrief. So if you remember Hänkelbrief, you will know the elements that come in pairs. So hydrogens come in pairs, H2. Oxygen comes in pairs, O2. There's another way to remember this, and it's a saying that goes, have no fear of ice cold beer. Now that one doesn't work out so well because when you look at the word beer, which is supposed to be bromine, beer starts with Be, which would be beryllium. And ice starts with iodine. I guess that works. Have no fear of ice cold beer. Cold starts with CO, that would be cobalt, or C for carbon, not chlorine. So you can change the have no fear of ice cold beer to have no fear of ice clad bratwurst, because you can always grill them. All right, now this is a compound. Now why is this a compound? We've got 2 different symbols. And we have a specific ratio of atoms. And really, it's a specific ratio of atoms of the elements. Okay, so that one's done. Let's move along. So the next section, we talk about physical properties, and the goals are to identify several physical properties of common substances, relate density to the volume and mass of a substance, and understand the difference between extensive and intensive properties and give examples of them. So here, the density is actually going to become part of a lab that we're going to be doing next week. And for that lab, you're going to need to have a scale. You're going to need to have the graduated cylinder. What else are you going to need? You're going to need the pennies and the dimes. So you've probably seen that message a number of times, at least twice, where I told you need 50 pennies minted after 1983 and 50 dimes. The dates on the dimes don't matter. Usually you can go into a bank and get those. You get a roll of dimes, it's $5. And the cool thing about that experiment is when you're done, you can spend the dimes. Okay, so let's take a look at some physical properties. These are things that can be observed without changing the matter into other types of matter. Okay, so that means you can do this without changing it into something else. You can check out the property of hydrogen peroxide without turning it into water. And these are examples of physical properties: density, color, mass, volume, temp. Temp is my way of saying temperature because I'm lazy about saying whole words. And the reason we're interested in physical properties is that they're often used to distinguish between types of matter. If you have something that's a solid and something that's a liquid, you know the solid's probably not water if you're looking at it at room temp, okay? So we like to know the properties of compounds and of substances so that we can tell them apart. And here, different types of matter will have different sets of properties. So there's a problem that's in this particular section. And it states the following: a piece of polypropylene rope used for water skiing floats on water, whereas terephthalate polymer from a soda bottle sinks in water. Place polypropylene, the terephthalate polymer, and water in order of increasing density. So here's the deal with density. Less dense floats on more dense. And the opposite is true. More dense sinks on less dense. So if we know that the less dense floats, we can take a look at these and see what happens. So here, the rope floats on water. So when we want to put these in order of increasing density, we want to go from low to high. So here, definitely on the low end is going to be the rope, and on the high end is going to be the water, because the rope floats on water. Okay. Now next we have the terephthalate polymer from a soda bottle sinks in water. So here, even higher yet, is going to be the soda bottle, which is the terephthalate polymer. So here, when we look at the density of these things, we would say the rope is less dense than the water, and the water is less dense than the soda bottle. Okay, so we all recognize these symbols from math. This would be less than. And the words don't really matter. What really matters with this symbol is you know that this side is small and this side is large. And if you write the symbol backwards, this is large and this is small. And if you write the symbol like this is large and this is small. The idea here is the larger opening means the larger side. The smaller opening means the smaller side. And I was actually told by a mathematician that this symbol, these symbols used to be like this. So this was large and this was small. And then I was thinking, oh, so that explains equal. The sides are the same amount apart. So that's where equal comes from. I love it. Math is great. Okay, moving along. Extensive and intensive properties. An extensive property is one that depends on the amount of matter you have. So mass depends on the amount of matter you have. You can have a massive sandwich or a not so massive sandwich. A large volume of sandwich or a small volume of sandwich. It depends on how big your sandwich is. So some properties just depend on how much of the matter you have. Some don't depend on the amount of matter you have. For instance, you could think about taste. You know, you have a small sandwich, it tastes great. You have a big sandwich, it tastes great. That would be an intensive property. Here are more common intensive properties that depend only on the type of matter, not on the amount. The color, a little bit of gold is gold colored, a lot of bit of gold is gold colored. Density, a little bit of gold is more dense than water and it'll sink in it. A lot of bit of gold is the same density, it'll sink in water. Temperature, boiling point, and melting point. I heard a ding, which means my phone went off. I got to turn that darn thing off. I'm not phone savvy. I got a smartphone, but I'm not a smart user. So extensive depends to the extent of the matter you have. Intensive is an inside property that doesn't depend on the amount of matter you have. That's kind of the way I remember them. Extensive, extent of the amount. Intensive, and it's inside thing. Okay. All right, so here's a problem. A sample of mercury has a shiny surface, melts at 234 K, has a mass of 27.2 grams, and a volume of 2.00 centimeters cubed, and has a density of 13.6 grams per centimeter cubed. Which of these properties are extensive and which are intensive properties? Okay, So I started off with liquid, which the book doesn't, because I thought, well, that is a property of this thing. It's the state of the material. So does it, mercury being a liquid, depend on how much you have? And the answer is no. So this is intensive. How about the shiny surface? Nope, that depends only on the material, not how much you have. Intensive. Then it melts at 234. Turns out that that's also intensive. A little bit of mercury will melt at 234, a lot will melt at 234. How about the 27.2 grams? Well, yeah, that does depend on how much you had. If you had less mercury, it would weigh less. So this is extensive. And the volume is extensive. And this is an interesting one because this is mass, which is extensive, over volume, which is extensive. However, this is intensive. Why is this an intensive property and it does not depend on the amount that you have? And the answer is, if you were to double the mass of your mercury, you would also double the volume. So when you double them both, the ratio stays the same. So density is intensive. Okay. Now remember, if I'm going too fast for you to write this down, your job is to take a screenshot or to snip it and save it. Okay? So the amount of time I'm spending on each of these should give you plenty of time to do a screenshot or to snip it and save it. Or you could go back and watch it again. I can't even watch it the first time. Okay, next we have physical and chemical changes. And this is a kind of a goofy area where a lot of people kind of get confused. I'm hopefully going to reduce the amount of confusion, although probably won't be successful completely. The goal is to explain the difference between chemical and physical changes and identify several chemical properties of common substances. Okay, so let's start off with the physical change. This is a change in a physical property. And you're going to see me use this symbol a lot in this class, a triangle. That is the Greek symbol delta. There's two deltas. There's an uppercase delta and a lowercase delta. I'm not sure which this one is, but it means change in. So this would be a change in temp, a change in mass, a change in volume. So T for temp, M for mass, and V for volume respectively. You'll notice the V looks taller than the M because it's an uppercase, whereas the M is a lowercase. You could have a change in state. So normally when you have these changes where in these physical properties, you could write something like this. This is an example of a change, a physical change. Here, gold, solid, turning into gold, that's a liquid. So this is melting gold. That's a physical change. Okay. Now, chemical change, on the other hand, is a change in chemical properties. So that might include something like precipitation, which we'll be learning about, oxidation, reduction, corrosion. More importantly, for now, you want to know that a change in chemical properties means it's a change in formula. Now, if we look at above, do you see that the formula for gold is AU, whether it's a solid or a liquid? So here, during this change, there's no change in formula. Therefore, the above is not considered a chemical change. It's considered a physical change. No change in formula. Okay? Just to backtrack a little bit, gold is not one of those elements that come in pairs, and that's why you don't see a little 2 behind it. Okay? All right. So here, for a chemical change, you're trying to change the matter of one type into matter of another type. So that means if you have another type of matter, it's going to have a different set of properties. Do you remember how we talked about we like to look at properties because different matter will have different types of properties? Well, here we're going to see that in this chemical change that you are going to have a different set of properties. Here, this is a liquid, and you make 2 different things. One is a liquid and one's a gas. Now, is that a physical change that's happening? Absolutely. But why do we call this a chemical change? And the answer is because the resulting matter has a different set of properties than the beginning matter. And really, it's a different chemical set of properties. And ultimately, if we have an equation like this is called a chemical equation, we can tell there's a chemical change because the formula has changed. H2O2 is not the same as H2O. They represent different compounds, so this is a chemical change. This also becomes O2, and you can definitely tell that these two formulas are different. Now, one of the things that you may be asking yourself, well, what about this O2 and H2O2? Isn't that the same O2? And the answer is no. When you write the symbols right next to each other, that means that they are chemically bonded together. Chemically bonded together. So here, these two hydrogens and these two oxygens are chemically bonded together. Here, these two oxygens are chemically bonded together, but also there aren't hydrogens chemically bonded here. So here, we know that this is a different formula than this, not just the O2 separated, because there's no space here, and these are chemically bonded together. So how do we indicate in a formula or in an equation like this that, hey, this is not part of what comes before? You put a space in between them or a plus sign. You put some sort of thing like that in between the symbols of the elements, and you know you're talking about a different substance. Okay, so physical change, a change in physical property, chemical change, change in chemical property. How, when you're looking at formulas, do you tell the difference between the two? The answer is, in a physical change, the formula does not change. In a chemical change, the formula does change. Okay? Now, how do you tell if you're not able to see the formulas of things? Because I got to tell you, I walk around town and I don't see labels on things that say, oh, this is what I'm made out of. So how do you tell? And the answer is, well, you have to take a look at the material before and afterwards and see if it has the same chemical properties. So with the gold here, solid to liquid, how would you see if those had the same properties? Well, one of the things I would do if I had the solid and the liquid is I put them both at the same temp. Because if they're both at the same temp, they should be the same state. That's the easiest thing to do. Cool them both down to room temp. They should both be solids. And then try and do other things to them. They should look the same. They should smell the same, although technically we don't like to smell things in the chemistry class because that's how you lose your sense of smelling. Okay, so that's the kind of thing you would do to see if it were chemical versus physical change. Start comparing properties and do it all at the same temp so that they should have the same properties throughout. Okay, moving along. Chemical change versus physical change. Actually, I said that in reverse. Physical change versus chemical change. Both involve some sort of change in physical properties. How do you tell the difference? You can see I got ahead of myself with the last slide. Basically, when you're looking at the formulas, a change in formula means a chemical change. No change in formula means a physical change. So that's actually pretty easy when you're looking at the formulas. Okay, so we're looking at a problem here. Identify each of the following as being either a physical or a chemical change: boiling water and rusting of an iron nail. Now, something else I didn't tell you, which we'll talk about during this problem, is there are other ways to often tell whether you have a chemical or physical change. Now, for boiling water, we know that we have water turning into steam. And water doesn't carry around a formula that says H2O on it, and neither does steam. So in this case, how might we tell if these are the same? And the answer is, you know what I'd do? I'd collect the steam, put it into a container and cool it down and see what it looks like. And if it looks like water, I would suspect, oh, the steam is just water. What do you call it when you take that gaseous steam and you turn it into water? It's called condensation. So that wouldn't be enough. You'd have to condense it and see that it's liquid water or looks like liquid water, and you would compare the two samples. So one of the things you could do with each of the two samples, the water itself and the steam that you've condensed is you could boil both of them. If they both boil at the same temp, they might both be the same thing. You could do something else to confirm that they're the same thing. You could take both samples and freeze them. See if they both will freeze at -1 degree Celsius. They both freeze at that temperature, you'd be even more convinced that it's water. So for this, what I would do is I would collect this and then compare properties. Okay. Now, a kind of go-to for a lot of scientists when they talk about is something a physical change or a chemical change is it fairly easy to reverse? Now, this doesn't always work, but it would work for boiling water. Would it be easy to reverse the water turning into steam? That is to say, to take the steam and turn it back into water. That's fairly easy. You just cool the steam down, okay? But that's not true for all physical changes. For instance, if you have a tomato and you cut it in two, that's a physical change. Is it easy to reverse that process and reassemble the tomato? No, not so much, okay? But it's not a chemical change. So here, this is going to be a physical change. Fairly easy to reverse. Okay, now the rusting of an iron nail. So here's your iron nail, and when it rusts, what happens is it starts to get these patches of red on it. So here's my patches of red. And then what happens over time is your nail ends up looking kind of like this. It's really rough on the outside, and you end up with this patch of red material at the bottom of it. And if you actually take a look at the properties of this red material versus the material of an unrusted nail, you notice that the red material is more like a powder than the nail. The nail you can bend. This stuff, if you scrape it off, it's crusty and brittle. So when it has a different set of properties, and this is all at room temperature, you're pretty convinced that this is a chemical change. So notice here, I'm even looking at physical properties to see if it's a chemical change. This material, this reddish material, does not have the same properties as the original nail. So this, we're going to say, is a chemical change. Why? Hard to reverse. I mean, if we could unrust nails, you know darn sure we would unrust our cars. Hard to reverse. And here you end up with matter that has a different set of properties. Okay, and of course, the easiest types of properties to look at are not the chemical properties, it's the physical properties. Because physical properties are the easiest thing to look at to help us distinguish between types of substances. Okay, next we're going to be looking at energy and some basic principles. So the goals is to identify types of potential and types of kinetic energy, recognize and apply the law of the conservation of energy. Really, we're going to be doing this, recognize and apply the law of the conservation of energy when we do a lab about specific heat, where you will also need your dimes and your pennies. Okay, so the two types of energy are kinetic energy and potential energy. And you can see here that I am starting off with kinetic energy. Kinetic energy is the energy of motion. And here are 4 separate examples that all differ from one another a little bit. So one example is something moving from one place to another, like a ball that's being thrown or a river flowing. Now I'm going to back it up a bit and say that when we look at potential energy, I also have 4 examples. And on exams, I love to put questions down that say, give me a list of properties or give me a list of types of kinetic energy and types of potential energy. I love to put those things on exams. And a lot of times you want to bounce off of one list to get the other list. And we'll see how we can do some of that here. So here, if we take a look at kinetic energy, something moving from one place to another. So the ball being thrown and the river flowing are not two types of kinetic energy. They're one type, something moving from one place to another. Okay? And this is a problem on the test also. When I ask for examples, I'm also given examples that represent the same thing. So this is one example of a kinetic energy, something moving from one place to another. Sound is another type of kinetic energy. It's motion energy. Now you might think, well, with sound, air is moving from one place to another. And the answer is not so much. Here's what I want you to think about with sound. Imagine that you have a rope tied to a wall, and on this end you have a person who's holding onto the rope and they're swinging that rope. So they're sending a little wave at the wall, okay? Now, that little wave, as it travels to the wall, does it have energy? And the answer is absolutely. Stick your face right here and you're going to find out just how much energy that rope has. Well, did the rope move? And the answer is no. The rope is still between the wall and the person. The rope hasn't moved from one place to the other, yet energy has been transferred down the rope. Those little humps of rope are pulses of rope. That's the same way that sound works. When I speak, I'm pulsing the air. And when the air pulses, it'll pulse against your eardrum. And based on the vibrations in my throat, it'll make the vibrations in your eardrum a little different so that you can distinguish words. It's pretty fantastic. I'm not sure if all animals can distinguish words like we can. You know, it may very well be that Snoopy does hear a womp, 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 womp. I don't know. Okay. But nonetheless, the air pulses. And the proof of that is simply this. If the air actually moved from place to place, all of your teachers should be dead because they talk up a storm. And with all that talking, they should be pushing all the air away from them, and they should have died from suffocation long ago. So unfortunately, sound does not move, it pulses. Wait, I'm a teacher. Fortunately, sound pulses, it does not move. Okay, heat. How is heat different than something moving from one place to another? Usually when we talk about heat, we're talking about the vibration of atoms. So imagine Snoopy dancing on his doghouse, but he's not moving anywhere. That'd be like the vibration. So molecules, when they reach absolute zero, have no kinetic energy. Absolute zero is the lowest temperature you can have. So they don't even vibrate. As soon as you increase that beyond 0 Kelvin to something, they start to vibrate. And the higher the temp, the more they vibrate. And eventually, if you increase the vibration enough, or the heat, I should say, if you heat them up enough, they will start moving relative to one another. So we have a different type of kinetic energy there. But heat, we usually think of being as the atoms vibrating. And then there's electricity. Electricity is kinetic energy because electrons flow from one atom to another. But the interesting thing about it is that you don't really notice that the electrons are flowing. It's kind of like sound in a way, because the electrons move from one atom to another, but there's always an electron to replace the electron that's moving. So it's almost like musical chairs, but there's enough chairs for everybody. So the electrons move around in a circle. And how do you stop your I don't know, your record player from playing? You unplug it, you interrupt the flow of electrons, okay? Or in other words, you turn off the song and they all sit down. Okay, so 4 types of kinetic energy. Moving from one place to another, sound, heat, and electricity. Now, if we look at potential energy, there are 4 types. One type is energy due to position and gravity. So you can see in my drawing here, I've drawn a person This happens to be my Facebook profile. It looks just like me. And here you can see that I have a book above the person's head, magically levitating. That book has potential energy. And if we were to let that book go, that potential energy would turn into kinetic, and then it would hit the person's head and it would turn back into potential. Now, if you take a look at this book here, which is much farther from the top of the person's head, that has more potential energy. So the potential energy here is due to naturally the mass of the book and how far away it is above a person's head. So how far apart? Okay. Interesting thing about gravitational energy is it depends on two things: how close two things are and how big they are. So for instance, the gravitational energy you feel on the Earth is 6 times greater than the gravitational energy you'd feel on the moon, because the moon is 6 times smaller. But also the amount of energy depends on how close they are together. So you feel a lot of gravitational energy with the Earth, but even though Jupiter is much larger than the Earth, you don't feel the gravitational energy. And the reason? You're too far away. Okay? All right. The next type, the book says, would be a stretched spring. I include a stretched or compressed spring. They both have potential energy. So the stretched rubber band has potential energy. And I know that these little Nerf guns have like a little spring in them where you put the little Nerf dart in there and it compresses the spring. And we know that those Nerf guns tend to have a lot of potential energy. So a compressed or a stretched spring. Next, we have chemical potential. This is potential stored in bonds. So when the chemical reacts chemically and bonds are broken and the bonds are remade, if there's any leftover energy, that energy is released. And this is done to great effect. So for instance, there's something called TNT, trinitroglycerin. There's something called dynamite. And there's stuff called nitroglycerin. Nitroglycerin is the stuff you see in those old Westerns where it's a liquid. They're moving about in a wagon and they know that it's really dangerous. And if they run over a rock, this might explode. And of course, they run over a rock. Dynamite is simply nitroglycerin basically infused into small particles like originally they tried sawdust and then eventually are using diatomaceous earth. And just by putting the nitroglycerin soaked into some material, it makes it safe enough for you to carry around in your pocket. Problem with dynamite is that the nitroglycerin tends to seep out of whatever it's soaked into, and then you have those droplets again, and those droplets are what are very volatile and dangerous. I should say explosive. So if you ever come upon a cave and you find some dynamite and it's sweating, that is, has liquid droplets on the outside, you better get your butt out of there because that stuff is dangerous. Okay, so we have chemical potential. And then there's electrostatic, which sounds like electricity, but here, this is due to charge separation. It's not due to electrons flowing. So here we're going to learn later that there are 2 types of charges. There's something called positive charge and something called negative charge. And it turns out that positive charges are attracted to negative charges, and like charges repel. So that means a negatively charged object would repel another negatively charged object, and a positively charged object would repel another positively charged object. But positives and negatives are attracted to one another. So these are your 4 types of potential energy. Energy due to position and gravity, a stretched or compressed spring, chemical potential. Let's go ahead and put down chemical bonds because that's what it's really all about, and electrostatic. Okay, moving along. Conservation of energy. This is something we'll be using later in a specific heat capacity lab. Conservation of energy basically tells us that well, I should say the law of the conservation of energy tells us that energy cannot be created or destroyed, but it can be converted. So for instance, we have the potential energy of the book over the person's head. We can move the book higher above the person's head. When it's moving, that's kinetic energy. And when the book is higher above the person's head and no longer moving, it now has potential energy again, but more potential energy. The amount of kinetic energy you put into the book ends up being the more potential energy that you have in the book. So you can turn potential or kinetic into potential, and you can also turn potential into kinetic. Okay, it's like the Nerf gun. You put the little dart in, you compress the spring, you got potential energy. How do you release it? Squeeze the trigger. Okay, all right. And then here, this is the basically the statement that the law of the conservation of energy. That is to say that energy cannot be created or destroyed. The total energy of the universe is constant. And this is what we're actually going to be using when we do specific heat capacity problems. This E is really an epsilon. It means sum of. And when I say sum of, I mean S-U-M, not S-O-M-E. So you sum all the Q's of the heat changes that are happening, and that's supposed to equal 0. And this is a reflection of the energy of the universe is constant. We're going to find out that you can actually assign sign to heat. It's either positive heat or negative heat. Has nothing to do with like and I should say, if it's positive heat or negative heat, we're talking about positive energy or negative energy. This is not some metaphysical guru baloney stuff where there's positive energy and there's negative energy. Positive energy just tells you that's energy that you have to put into something, and negative means it's coming out. It's a designation of direction of energy flow. Okay? All right. So now that's the end of chapter 1, pretty much. And this next section we're going to dive into is a review. It's called The Tools of Quantitative Chemistry. And this is going to be a very quick review. We're only going to get through probably mathematics of chemistry today. But again, I'm going to go through this very quickly because the understanding is you've dealt with this before. All right, so let's get going here. Units of measurement. Goals. Use the common units for measurement in chemistry and make conversions, such as from liters to milliliters. SI base units. So SI stands for System International. This is my attempt at trying to write out how it's spelled because I think it's French, but I probably failed miserably. But that not mattering a whole lot. Let's take a look at some different properties. So one property is mass. Mass is the amount of matter in something. And let's talk about mass very quickly. When we talk about the amount of matter in something, that amount of matter does not depend on where the mass is. So for mass, we usually measure things in grams, and it's not the same as weight. Weight is your gravitational attraction to something, okay? So your weight on Earth is 6 times greater than your weight on the moon, but your mass on Earth is the same as the mass on the moon. Because again, mass is the amount of material. Weight is your gravitational attraction. So I do have a weight loss method number 1, in case you wanted to lose weight. It's to move to the moon, you will weigh less. All right, so mass is the amount of matter in something. The SI unit is a kilogram. And to give you an idea of what a kilogram is, it's 2.2 pounds. In a chemistry class, we are not going to use 2.2 pounds of any chemical for a reaction. So it's a rather large amount. The abbreviation of kilogram is a lowercase k and a lowercase g. Now in the lab, we tend to use the gram or the milligram, which is abbreviated as a lowercase g or a lowercase m and a g. Now, for length, the SI unit is the meter, which is about the length of your arm. The abbreviation is a m. And we measure things in either the centimeter or the millimeter in the lab. This is a very long length for anything we might measure in chemistry. Time is the second. The abbreviation is an S. And for the lab unit, it's also a second, and the abbreviation is an S. Temp. The SI unit is the Kelvin with the lowercase k. Well, actually, I think it's an uppercase k, not a lowercase k. And here in the lab, we use Celsius or Kelvin. I never understood this. They always make this word lowercase when I write it out, but it's named after a person. Kind of weird. Amount is the mole. This is the abbreviation for a mole. Don't use it because people look at that and they think molecule. Okay, so here's the lab unit we use for amount, mole. I've also added energy here. It's not really one of our SI units, but we're going to add it. Energy, we have the joule. Lab unit, we use the calorie. Now, this is not really an international base unit, but I'm going to add it. Volume. So volume, we often use the liter. The abbreviation is an L, but in a lab, we more often use the milliliter. Now, the reason this is not a base unit is because a milliliter is a centimeter cubed. In other words, it's a length times a length times a length. So a volume is actually a derived unit, not a base unit. Okay, so this is a derived unit, and both of these are actually derived units. We could also call them complex because they're made out of more than one base unit. Okay, moving along. Let's look at temperature. You want to be able to make different types of temperature conversions. The English way of measuring things is Fahrenheit. I think we may be the only country in the world that uses Fahrenheit. The metric term would be Celsius for measuring things, and it's far more common when you're watching news from other countries for them to report the temperature in Celsius. And in chemistry, the base unit would be the Kelvin. So you want to memorize both of these equations. If you want to convert, this first equation is defining the temperature in degrees Fahrenheit. And here's what the equation looks like. You take the temperature in degrees Celsius, multiply it times 9, divide it by 5, and then add 32. Now, the reason this says degrees Fahrenheit and the reason this says degrees Celsius and this says degrees Celsius, degrees Fahrenheit, is that when you put the temperature here in degrees Celsius, the Celsius cancels out, the unit ends up being degrees Fahrenheit, and degrees Fahrenheit plus degrees Fahrenheit gives you degrees Fahrenheit. So kind of a simpler way to think about that is just say that, well, if you want the temp in degrees Fahrenheit, multiply degrees Celsius times 9/5 and add 32. We'll be coming back and looking at this formula later when we talk about significant figures. If you want to turn something into Kelvin, you take the degrees Celsius and add 273.15 K. So you want to memorize this. This is not exact, it's rounded off, but you do want to know that value. So room temperature is roughly 20 degrees Celsius. So that means it's 293.15 K. That would actually be considered to be a very warm room. Here's something else that you want to memorize, prefixes. These are numerical amounts. And the prefixes I want you to memorize, I've cut the bigger one off out of the book and the smaller one off out of the book, but I'd like you to know these: the mega, the kilo, the deci, the centi, the milli, the micro, the nano, and the pico. Their abbreviations are as follows: an uppercase M, lowercase k, lowercase d, lowercase c, lowercase m, lowercase mu, which is a Greek letter, and lowercase n and lowercase p. So this is a m, if you will, a mu. To me, when I draw it, I always think I'm going to draw a U with a long tail at the beginning. The amount for each of these is that a mega is 1 million. So a megabyte is 1 billion bytes, or excuse me, 1 million bytes. Kilo is 1,000. So a kilobyte is 1,000 bytes. Deci is 1/10, and you can't have a decibyte because the smallest unit in computers is a byte. A deci is 1/10, a centi is 1/100th, a milli is 1,000th, a micro is 1 millionth, a nano is 1 billionth, and a pico is 1 trillionth. So you want to memorize all of these, but these aren't very useful because we use these in calculations. So what is a million? 10 to the 6. What is 1,000? 10 to the 3rd. What is a tenth? 10 to the minus 1. And so forth and so on. So you want to memorize these numbers. And an interesting thing to know about these numbers is that if the exponent is positive, it's bigger than 1. If the exponent is negative, it's smaller than 1. So for instance, this guy here, kilo, that's definitely bigger than 1. Deci, that's definitely smaller than 1. Okay. Now, here's an example of how you might use a prefix. If you had a centigram, that would be 1 times 10 to the minus 2 grams. If you had a centimeter, that's 1 times 10 to the minus 2 meters. And just for fun, I put a centidog is 1 times 10 to the minus 2 dogs, and a centipede is 1 times 10 to the minus 2 peds. Now, the way you get this is you just start off with something. So I'm going to start off with, let's talk about a nanometer. 1 nanometer is 1 nanometer. You can't argue with that. If someone argues with you about that, you need to just kind of walk away slowly and try not to upset them because they're crazy. Now, since these nanos represent a particular amount, we can actually substitute a number for one of the nanos, and you get 1 nanometer is 1 times 10 to the minus 9 meters. And this is something we'll be using in the future. These types of things, they're called conversion factors. And this is a conversion factor between a prefix and, so a unit with a prefix versus a unit by itself. Another great question here is, well, how do you know that that's not a milli? And the answer is simple. When you have a letter by itself, it's a unit, not a prefix. When you have a letter with another letter, one of them's a prefix, the other's the unit, you always begin with the prefix, hence before, prefix, okay? All right, so make sure you memorize these. So here we're going to take a look at a problem where we're going to actually use these ideas. Distance between an oxygen atom and a hydrogen atom in a water molecule is 95.8 picometers. What is this distance in nanometers? Now, what I'm about to show you here is the type of work I would expect to see on an exam. If you came out and just wrote the answer down and it was correct, and that's a 10-point problem, I'd give you 1 point out of 10. You need to show me the work to get the other 9. And the deal is, if you show me the work and you don't get the right answer because you screwed up with the calculator, I'll probably give you a passing grade on that problem. Can't give you a perfect grade if you don't get it perfect. Okay, so here, I want to convert 95.8 picometers into nanometers. So I know how to convert from the prefix with unit to the unit alone, and I know how to go from the unit alone to the prefix unit. So here, if I want to get the conversion between a picometer and a meter, I start off here. 1 picometer is 1 times 10 to the minus 12 meters. And you can see this is just a very quick way of writing it out slowly and figuring out that it should be 10 to the minus 12. But once you memorize those things, you don't need to do this anymore. 1 nanometer is 1 times 10 to the minus 9 meters. Now, how do I use these conversions down here below? Well, number 1 means I'm going to use this conversion first. For this conversion, I want to take one side of the equation and put it on the bottom, and the other side and put it on the top. How do I decide which side to put on the bottom? And the answer is, I put the side on the bottom that's going to cancel with what I want to cancel. I want to cancel picometers, so I put picometers on top, on the bottom. So that means I put the other side on top. So this would be converting from 9.5 or 95.8 picometers to meters. If I stopped there, I'd be done and I'd have it in meters. But I don't want meters. So I want to get rid of that meters, but I want to get nanometers. So that means I'm going to put my 1 times 10 to the minus 9 nanometers on the bottom, and I'm going to put my one, oops, excuse me, I screwed that up. Do you see that? Got to be careful. And I'm going to put my 1 nanometer on top, and that allows us to complete the conversion. So in our calculator, how does this look? I'm going to show you that. This is the calculator I recommend you buy because it's solar, it's cheap, and it's very easy to use. So watch the buttons as I push them. I'm going to put 95.8, and I'm going to multiply by 1 times 10 to the 12. So I'm going to do this times, and then I'm going to write 1 second EE. And then I'm going to put negative 12. So the negative is right here inside of that parentheses. And when you see that 1E negative 12, that means literally parentheses 1 times 10 to the minus 12. So notice I don't have to put the 10 in there. And what's really neat about this is it treats it like it's a big parentheses. Now I'm going to put divided by 1 second EE negative 9. So again, that 1E negative 9 is 1 times to the minus 9 in parentheses equals, and we get 0.0958. And what are the units? Well, everything canceled except for nanometers, so I'm done. So let me show you a wrong way to do this. So a wrong way would be to put 95.8 times 1 times 10 to the caret negative 12. So many of you know how to do this. 10 to the minus 12 means 10 to the minus 12 divided by 1 times 10 caret negative 9. So let's see what answer we get here. And we get 9.58 times 10 to the minus 20. The reason this doesn't work is because when you use the caret, it doesn't put parentheses around things automatically. You have to put the parentheses in. So don't use the caret. I only use the caret for one thing, and I'll tell you about that when we get there. Use that E thing. Okay, now as far as your calculators go, here, this is a TI-30X. They were on sale at Target a week ago for like $10.99. Great deal. Not on sale, they're like $14.99. I'd pick one up because even if you drop it and break it, you can buy another one very inexpensively. Now, if you have a TI-83 or TI-84 or anything like that, and you're comfortable with using it, fine, you can use it. The joke is, and I've already told it to you, you want to use a TI, know how to use it. That's kind of funny, right? Okay, not so funny. And then the new joke is you don't want to buy a Casio. Oh no, I don't know how to use it. Okay, so there's that problem. Now, I can see that it's already 1 o'clock. So what I'm going to do here is I'm going to stop here. I'll pick up from energy units next time. And on Monday, you can expect me to go through the rest of this section, the review, and then possibly move on to the next section or next chapter. Okay, so that being said, I'm going to go ahead and stop the recording. And I'm going to see if anyone has any questions.